Today we will really go through the security proof. I will nonetheless briefly summarize what we have seen yesterday, because we will need some elements from yesterday's lecture. But let me briefly start by explaining why is it actually a challenge to prove security. And we have probably seen that now in several instances. You have even tried, or maybe successfully, done kind of part of a proof with Norbert. But what's the, let's say, conceptual reason why security proofs are hard? And the reason is basically that if you look at the QKD scheme, we are using a channel, and for a quantum channel, I have these wiggly lines from Alice to Bob. And normally, when we do standard quantum information theory arguments, we can say that, let's say we use the channel many times. I send a signal, then I send the next signal, I send the third signal, and the signals will individually arrive. The first signal here, one will arrive as signal 1, the second will arrive as signal 2, 3. Now, if in a cryptographic setting we have an adversary who may, in an arbitrary way, corrupt these communication channels, or the channel. I mean, it's one channel over time. And now this means, if I throw this into the picture, that what happens here could be an arbitrary operation, like some operation. Of course, it's constrained by some causality. So, for example, the adversary will not be able to output at the time 1 something that Alice only tries to send at time 3. But the adversary could, for example, store something that Alice sent at time 1, keep it in a quantum memory, wait until the second signal arrives, then perform some arbitrarily complicated operation on them, send something further that depend on the output, or maybe store some other results further, and then put stuff later. So this ends, so the state you have here, the description of what these systems are, could be, for example, entangled, even though you send these signals individually. And now a security proof entails making sure that whatever this operation is, whatever complicated ideas the adversary has in mind, it will never lead to a breach of security. So we have to go, it's a kind of an all quantifier. We have to say for all possible attacks that an adversary can perform. And this, I just now described, this is really a large class of possible attacks. It's in quantum information theory terms, you could say it's any completely positive map, if you want to describe it mathematically, or sequence of completely positive maps that we can apply here. And for any of them, we have to prove it's secure. And that, of course, we can never go through that whole space individually. If I told you what the adversary would do, it would be much, much easier to prove security, because you could write down a concrete quantum state and say, okay, let's calculate whether the key is correlated to that state. But the challenge is really to have a method, or to have a set of tools that allows us to talk about all these states at once. And that's basically why it's not easy to prove security. I should also emphasize again, because that's sometimes, I mean, you know that, of course, very well, everyone here, but sometimes when you talk to people, they don't realize that security is not something you can observe. So if you implement the QKD scheme in a lab, and the message, maybe you use it at the end to send a message from A to B, and the message arrives correctly, that gives you a priori no indication that it was also secure. Because what would you need to do to actually prove security experimentally? What you would need to prove, so let's say you are an experimentalist and you don't want to rely on a theorist telling you that if you observe these and these parameters, then we have a proof that it's secure, if you want to directly see it. Then you would have to implement all possible attacks and see that for none of these attacks what comes out is correlated to the message. And that is, of course, again, an even harder task, because most of the attacks we are considering would be with today's technology not implementable, but we still want to have security against them. Okay, so that's just a short explanation for why these proofs are challenging, and why maybe if you look at things historically, it also took a very long time, and people are still working in certain cases on security proofs. So even certain commercial schemes like the COW protocol, that is a protocol used by ETH Contic in their devices, has no security proof at this point against general attacks. There are some limited proofs which say, let's assume the adversary is very nice and only applies operations here, and all these operations are also the same. It's called a collective attack. I don't know, this terminology is not that good, but it's meaning you do the same stuff on each instance of signal transmission. Then they have some arguments why it could be true, but in particular in the COW protocol that I mentioned, information is anyway already encoded into correlation, so that is also not really satisfactory anyway, even if the adversary was nice. So that's the situation. And now we will see, or I hope at the end of the lecture we'll see how this complexity gets reduced. So a big task in proving security is to reduce the complexity of this and say, we actually at the end don't have to consider all that. If we prove security against one particular, maybe a small class of attacks, this implies automatically by some general information theoretic statements that we have security against everything. So that's why if you wonder what theorists were doing all the 30 years, or it's now 40 years since the invention of BB84, that's really the challenge. And that also explains, by the way, why you cannot expect, for example, in the BB84 paper when it came out, that they would deliver a full security proof. Like there was a contribution to invent the protocol, and they had some arguments why it's probably secure, but then it required a lot of effort. And actually, the one thing we will see, even the step of privacy amplification, that was already a big challenge to understand that. And I will talk about that in a minute. By the way, Uli Maurer, I think you had the first paper on privacy amplification together with Gilles Grassard and Dr.
Yes, well, it was kind of the second. They had a paper and I pointed out that there was a problem. Then we wrote a paper.
So it was the first correct paper.
By the way, I would argue, but I won't do it, that it's still too limited. We may talk about it later.
Okay. So there's still a chance to have the first paper. Maybe you take that's what Norbert said. But he said, whenever you have a big contribution, you should make it not optimal so that people still have a chance to improve. So you were very nice. Okay. Now, just as a very brief summary of yesterday. So what we did, what were the main points? One of the things where we discussed the assumptions that enter QKD security proofs. I hope you remember them. I will now not make an exam on them, but it's someone said it very nicely, correctness and completeness. So the correctness means the formalism of quantum theory as, for example, described by, I think there are 5 axioms in Nielsen-Schwann, is correctly describing what happens in the real world in your not in the actual implementation, but it describes correctly what happens in real physics. And then there's another assumption which actually says the things you build, the devices, the photon sources and so on, are correctly built. So they're trusted, or they do what they are supposed to do. This is the second assumption. So the physical laws could be correct, but you just build a photon source that instead of emitting one photon, as required by certain protocols, emits statistically sometimes fewer, sometimes none, or sometimes more, then you're a priori in trouble, and you have to go back to the theorist and ask, don't you have a more flexible protocol that can tolerate random photon numbers, and then that's the way you proceed. There was also the completeness of quantum theory, which I illustrated with the Kish cipher. So this is the statement that any information that is potentially accessible somehow is also described within the formalism of quantum theory. And I said this would not be the case for thermodynamics. There's of course much more information, the position of molecules and so on, but thermodynamics as a phenomenological theory, not statistical mechanics. Really, the old-fashioned thermodynamics doesn't talk about these degrees of freedom, but they exist, and an adversary could exploit them. So quantum theory, however, is complete in that sense, and some people ask me after the lecture, what does this have to do with Gödel's theorem? So the completeness is not the completeness that Gödel considers. I should maybe more precisely term it information theoretic completeness. So the theory can model all information that is around in the setup. It doesn't have to do with completeness in terms as a logical system. And then, of course, the last assumption I mentioned, which is always anyway explicit, is that we start with an authentic channel, but I emphasize that because sometimes people forget that we need to start to have an authentic channel. Now, and by the way, the authentic channel is also necessary because if you look at the setup we have without an authentic channel, then there is no asymmetry between Alice, Bob, and Eve. And at some place, Alice and Bob need to have an advantage in order to overcome, or in order to establish a secret that is unknown to Eve. So one can actually probably also do a proof and show that authenticity, or at least some form of authenticity, is needed to achieve that. Okay. Now, the other part of the lecture was the security definition, and I will not write it down, but just to remind you in terms of this box that I've drawn, and I think there were two important points. Generally that, so the box that I've drawn is one that outputs keys to Alice and Bob, the same keys, which are also supposed to be uniform, but we said this specification may be relaxed, so if it's epsilon close to that behavior, it's also fine as long as the epsilon is small enough. And we also saw the epsilon can be interpreted as a probability of failure. And this really tells you how to choose the value. Maybe as an insurance company, it would allow you to calculate the price of an insurance if you know how large the damage is as well. And the other important thing was the adversary can choose the length of the key, and it could also even be 0. So we have no guarantee that a key is obtained, but if a key is obtained, then there is nothing leaking to Eve. Of course, Eve knows L, she gave it as an input. That's what was also emphasized in Uli's lecture. But in the case of the one-time path, but we have this already here. Eve knows how long the key is that Alice and Bob have established. So that was the part about the security definition. And then, we also finally talk a little bit about smooth entropies, and I will continue there. And of course, the other topic were black holes, but I will not talk about it. I'm not allowed to. So smooth entropies. So yesterday I gave a definition, not a definition, but I told you what is the operational meaning of that. So usually the logic is, and I will maybe later give the definition, so I will write down a definition, but this definition is actually, if you're working on the level we are now working on, where we use certain results which are already established in the literature. So we will, for example, talk about the two universal hashing lemma. But if you just use that result as a black box, which is fine, I think this result has been used so often and checked by many people that you can use it as a black box, then in the proof of the two universal hashing, it of course matters what is really the definition of this, for example, the smooth mean entropy, the technical definition. But in order to understand the security proof on the level where you use these things, as I said, as a black box, it's more important to understand what are these entropy measures in terms of their operational meaning. And that's why I gave that. And I gave it in the classical case. And I'll write it down a little bit differently so that you see a slightly different perspective, which may help. So H min of x and y is, you can interpret this as the number of bits after a suitable rearrangement. So this is not, you shouldn't think of x as a fixed bit string and it's the number of physical bits. You take x and sort it kind of, so you apply a function, extract certain bits, and this is the number of bits which are completely unknown, completely random, which means uniformly random, but there's always an epsilon up to epsilon. You now know what it means to be almost random up to epsilon. It's the trace distance, and we discussed that in the context of this security definition. which are completely random even if you know, or even if not, if you know, if you have access. So you already have y in your register, and you're asking what is x, and there are this number of bits which are completely unknown. And the max entropy is kind of the opposite end of this spectrum in the following sense. It's the number of bits which are not completely known. So not completely known is not the same as completely random, of course. There's kind of a spectrum. And again, up to epsilon, so you may, if something is known except with a fail, like you may get it wrong with a probability epsilon, that still counts as completely wrong. That's what I mean by this up to epsilon. And again, if you have access to y. So that's how you should think of these measures.
Can I ask a question? I was surprised to see your first definition of H-mean, because it seems like already derived definition. A more basic definition could be, what's the probability with which you can guess X, just guessing it given Y?
Mm-hmm. Yes.
Why didn't you use that definition? Doesn't it
not
make sense in the
really
quantum case?
It's supposed to be a definition. This is just a statement which should be as close to how it's best to think about it when we later use it. So I'm not claiming that this is in any way. So I will just write down the definition. And so I think what I maybe should say, the logic is, okay, let me write down the definition. And I will give so when I write x and y, I implicitly mean by that the things are classical. This is just a notation I use. And I emphasized yesterday that, of course, if you have this type of interpretation, it has to be classical. And that's also sufficient in the case of our application if x is classical. And y, of course, you can think, okay, you have instead of a classical y, some quantum system, some register, and then I could still write down the same thing. But now the general definition is, of course, works where A and B are arbitrary quantum systems. And so the definition looks as follows. And so first of all, you have to be aware that all entropies, I said that yesterday, are actually functions of the density operator, not of the stuff that is here. A and B is just a label of a system. And sometimes we write the density operator here as a little subscript, so it's a density operator over systems A and B. Of course, one usually doesn't, again, write A and B here, but I just do that here once so that you are aware of. We start with an object, the density operator on the A, B, and now there is a definition which basically is okay, this may be confusing that there's a maximum here. So the minimum in the subscript and the maximum are motivated by these interpretations, operational interpretations, because this is, as I pointed out yesterday, or as you can see from here, if you think about this, this is certainly never larger than that. And this maximization just has to do with, or maybe I actually write the supremum, because that's a mathematical definition that even applies to infinite dimensional systems, and there it's a supremum. And now the supremum goes over a set, and it's a set of all real numbers lambda. So this is something you now don't need to really understand. I write this down just that you have once seen it, and then I will tell you why, what about it is relevant and what not. But for completeness, let me write it down, so that you see at least what is this object we're always talking about. So I take some other density operator, rho AB tilde, and I require that this rho AB tilde is smaller as a density operator. So there's an order on density operators. Those who had quantum information courses know that. And then the operator that is an identity on A and an arbitrary density operator on B. So this means this is also a density operator. So all objects that, okay, end, I have to continue. Rho tilde AB is epsilon close, and let me just write it with this shorthand notation, to rho AB. And so you optimize over all these objects that are here, so over the lambda and the omega b, and you try to find the largest value lambda that satisfies this definition here. Okay, I hope I got the sign right, but some people here just did a QIT exam. Is this the correct formula? Otherwise, you have to complain. Okay, good. So that's the definition. So as I said, if you go into the proof of the leftover hashing lemma, for example, that I will show, you will have to work with that definition. But otherwise you don't. And so the logic now of my presentation, to come back to your question, was this is the definition. That's clear, so we start with that. And now, in order to understand what's going on, it's just useful to think in that way. And this is anyway an approximation in a sense, because it's, let's say, they're basically now, technically these are now theorems.
And I guess you will say something like this, that the upper definition would assume that one knows this state, and even then this would be true. And the idea of privacy amplification is that you don't need to know which state it is in the whole specification, and it always works.
Yes.
That's the trick and surprising thing about privacy amplification.
I mean, I would completely agree in spirit. I would say it in different words, because I would never use the word know a state, because the state is the knowledge itself.
Sorry.
Okay. But I mean, I know what you mean, and it's absolutely correct, yes. So let's now indeed turn, or before, okay, I will turn to the leftover hashing, but maybe it's better if I first tell you about certain general properties of these entropies. So this is now an entropy measure, and by the way, the max entropy can be defined in a similar way, but actually you can just define it, and that's the, I think, modern way to do it, by the relation that I showed yesterday, that for a pure state minus the max entropy is that. That was not the original definition, that was later a discovery, but now as we know that this is the case, we can just say that's a very simple way. We don't have to go into the, let's say, operator language. We can just express the max entropy as minus the mean entropy of the of A given the purifying system, and take that as a definition. But of course you always have a choice, what is the definition and what are derived statements, but I think this just keeps things more minimal. And these entropies, so first of all, the reason why they're used is really this operational meaning. And it's not a completely independent statement if I say these entropies also have very natural properties. So why is this not independent? Of course, if it has an operational meaning, the operational things are natural. So what do I mean by natural? If I ask you the question, so let me ask the question, what happens, for example, if, let's say, I have here the mean entropy of x given y. I had a similar question yesterday, and I have a mean entropy epsilon with the same epsilon of x given y and z. What can you say about the relation between these two? Sorry?
The first one is less equal.
Yes, I mean maybe it's a large. I mean you said less. I think it's larger than equal. And why is that? Now you can, of course, go into this technical definition and prove it mathematically. But you can also look at this meaning and say, okay, what does this mean? This means the number of bits in X that are completely uniform if I know Y and Z. And of course, if I now lose Z, it's certainly not the case that there are suddenly more bits that look completely random. And the same can be said for the max entropy, the number of bits I'm not completely sure about. I mean, are not completely determined. There was this word missing here. This only changes in one direction if I lose information. Okay, and actually this property holds also in the quantum case, and so I just write this by replacing this x and y by letters A in my convention, A, B, and A, B, and C. And this is called the data processing inequality. This is an extremely important inequality, and you probably, if you had a quantum information theory course, you at least should have learned this inequality for the von Neumann entropy. Okay, I'm actually not sure whether it's a standard material. So who has seen this inequality in the case of the von Neumann entropy? Okay, so many have seen that. And I should also make the point that this is a non-trivial statement also technically if you don't think of these operational interpretation. So actually to prove it for the von Neumann entropy, it took several years and very clever mathematical physicists. I think one of them was Mary Petruskay and the other Elliot Lieb, who worked with heavy operator algebraic methods to actually get to this claim. For the von Neumann entropy. For the mean entropy, it's actually two-line. It's an extremely simple proof. So I could show it here, but I will not spend time on that. If you like, you can do this as an exercise. You just take this definition and ask yourself what happens if you add the system C to this, and you will see that these inequalities are going one direction. So the proof is almost trivial. Now, the other important thing is there are so-called chain rules. And chain rules tell you how does the entropy change if I add, so this just tells you this is smaller, but now I want to, let's suppose I want to have something in the other direction. So I want to here a smaller than equal to this, so something like this. So a priori this is of course now not true, but I can make it true by adding a correction term. And the correction term is, okay, something like this, H max epsilon of C. And in the case of von Neumann entropies, you have, the chain rules are actually equalities. Now in the case of mean and max entropies, the chain rules are still inequalities. And they tell you if I add that much of information to what so let's suppose you initially only have B, and now someone gives you more information, you gain information, C, how much does the entropy here maximally decrease? And the answer is, it's the max entropy of the information you gain. So it's actually quite intuitive. If you think of this, how many more, so if you again think in these terms, how many bits can you potentially learn by gaining information? It shouldn't be more than the number of bits of information you get, and that's, in a sense, what this inequality says. So there are several chain rules, and actually this is not a chain rule, not an elementary chain rule. This is something that is derived from the chain rule together with the data processing, but that's a property we'll need. I will still call it a chain rule, because that's a vague expression, and we will need that. So these are properties that you have to know. And again, if you don't care about the proof of these properties, you don't need to know this definition. But that's something you should know, and I think this is intuitive to remember. And you see now already the use of this. If you think in these terms, it's very natural that these properties hold. I mean, they have to hold, otherwise these operational interpretations would probably be wrong.
But they hold exactly without correction term.
Aha, okay. No, actually, in certain directions, okay, most chain, it depends a bit on the details of how, actually, I was here glossing over something. So this distance measure here is not, in the modern definition, not the trace distance, but something called the purified trace distance. So one looks at the purification of the state, and there are now certain details, and depending on how you choose the details, some of the rules become approximations. So usually it's that one, so I didn't. So here, maybe I will in the following be more precisely write such a sign, and what it means, this is just for the experts, is the equation holds up to terms of the additive terms of log 1 over epsilon, which is usually negligible in security proofs, because epsilon is something like, as we say, 10 to the minus 8. So this is just a number like 40, and you're dealing with keys that are 10 to the 8 bits long, so this can be completely neglected. Okay, now the last property I need to state is what is called the quantum asymptotic. Oh, maybe I'll write it out. Quantum asymptotic equipartition property. But because this is a long word, it's usually abbreviated by QAEP. And this statement gives you a relation between the mean entropy and the von Neumann entropy. So let's suppose you have some state rho AB, and you have some epsilon, which is neither 0 nor 1. So it's just this, what is sometimes called the smoothing parameter. Then the following is true, that the von Neumann entropy, which Norbert defines, so I will not write down the definition, of evaluated for that given state, can be seen as an asymptotic limit. So you take the limit of m going to infinity of the mean entropy. But now the mean entropy is not evaluated on one system, but you assume you have now n, where n is this number here, copies of these systems A and P. So you should think pictorially, you have a system A, P, A1, AB1, you have a system A2, B2, and so on, until AN, BN. And I call this whole line here A1 to AN in the notation A superscript N. And here I call this B subscript N. And then I assume that all these systems are in a n-fold product state, so which means they're all independently prepared in the state rho AB. So that's what is sometimes called the IID situation. The IID, this stands for classical, I think this comes from classical probability theory, independent and identically distributed. Or actually I don't know the order of the I's. One of them. Okay. So that's a statement, and this statement now makes clear what I meant yesterday when I said the von Neumann entropy is a special case of the mean entropy. So it's really special in the sense that you only need the mean entropy as a basic definition, and you can get the von Neumann entropy just as a limiting case of the mean entropy. And that's also really the way you should think of von Neumann entropy. When you look at information theoretic scenarios like coding, I mean, this is relevant not only in cryptography. So you look at something like data compression or so, and you read the result, or Shannon, even in classical information theory, the channel coding theorem by Shannon. It makes a statement about the capacity of channels in terms of Shannon entropy, and the Shannon entropy is just this classical version of the von Neumann entropy. So everything I write here holds in particular for the Shannon entropy. And then this coding theorem only holds actually if you assume you use the same channel n times, and n goes to infinity, and each use of the channel is, so the channel, the noise model of the channel is such that the channels are independent of each other and identical. So the von Neumann entropy is really, usually when it appears, a sign that if you think of it operationally, it's probably somewhere some IID assumption that comes in. And that's actually the reason why in cryptography, a priori, if you think about, again, this scenario where we have, as I pointed out, normally not independence in our uses of channel, it's a priori actually forbidden to use the von Neumann entropy. It's just not good. However, what you did with Norbert was calculating the von Neumann entropy, and the reason is that we will find reasons why it's still okay to consider such states. And then it's exactly via this quantum asymptotic equipartition property that you relate the von Neumann entropy calculations that we did with Norbert to the mean entropy which will enter the security proof. So this is the reason, in a sense, why the von Neumann entropy calculations are still usable. I mean, this theorem together with another theorem that will tell you that we can work with these states. So that's just the overview. So now you have, this was a kind of small interlude into quantum information theory. This is also sometimes called one-shot quantum information theory because, or beyond IID quantum information theory, just to stress the point that we don't make the idea assumption. And I think, actually you said that once, that the IID assumption is kind of hard-coded in information theorists' brains.
That's it. I mean, historically, people would prove results, security statements in terms of entropy, but that only makes sense if you had IID in a certain sense. So you should always think in terms of, let's say, the statistical distance of your key, and not a statement about
Yes.
entropy and so on.
Yes. So I think the
It's
idea assumption.
justified because you build a communication system that you test it works. And
Right,
security
yes.
you can't
Yes.
see, you have to prove, as you also pointed out.
Yes,
So
right. So, and indeed, in information theory, it's probably in practice a good assumption because you can just make the assumption and then code with an actual channel. And if the code works at the end, you can observe, you can see that, you can check whether the message was correctly transmitted. And then you don't care any longer whether the model was really accurate, but probably it was then just good enough to get the result. But in cryptography, that would be a completely wrong way of thinking. As I said, you cannot know its ID, and you also cannot, when you see that the message was transmitted, correctly infer that you were right, because it could still be insecure. Okay, so that's now the part on information theory. Are there any, I mean, these are the basics we will also need for the proofs. Are there any questions about that? This was the maybe more technical part. So if it was too technical for some experimentalists, you can now just try to remember there were certain rules, and you can forget that definition. That was just for illustration purposes. Yes?
So then all of this is done also without the IID assumption?
Yes, so the idea, so everything I wrote here didn't assume the idea assumption, except here, this statement here, that comes in. Yes. Was that your question? Or?
So then, the fact that the ID assumption is there, does it matter at the end for the security proof?
Yeah, so what we will have to do, we will have to do a step, and I haven't done that yet, to justify why at the end, when we, let's say, at some point I need to relate, so everything I'm going to do now will still be in terms of the mean entropy, and I will not talk about the von Neumann entropy for a very long time, until almost the end. And then at the end I will say, now we can relate everything I did to what you did when you calculated von Neumann entropies with Norbert, and then I will say this we just do by using this theorem. But in order to apply it, I will have to argue that now we need to make this assumption, and we can a priori not make it, so we will have to do some work basically to justify that. Any other questions? Then let's move to the security proof. And that's, as I mentioned yesterday, a chain of arguments. And we start with a quantum channel. So I will now think, okay, one always has a choice between thinking about prepare and measure and entanglement based. But because what Norbert presented was prepare and measure, I will also stick with that so that it's in that sense consistent, but there would not be a large difference here if I move to entanglement based. So we have an insecure quantum channel, and we have an authentic classical channel. And we assume that the quantum channel can be used n times, and the classical channel is a resource that we have available as much as we like. And now, in a first step of the protocol, not of the proof, as I said, we will go from the other direction, we will turn this into something where a state is distributed, A, B, E, and I will now summarize, so two steps I had yesterday, I will summarize into one. I thought it's better to do that. I can, of course, always two steps in one if I like, but in the protocol, there will be two steps, but as a proof, I will do it in one. And we still keep the channel. So we will achieve that we have this, but we will achieve this in a way, I shouldn't write A, B, I think I had X and Y. And there's also a guarantee, so we achieve this with the additional guarantee that the mean entropy of X given E is above a certain threshold, T. And that will, to be more, because we will have different thresholds, I will call this threshold X given E. So this is just some number that we will later have to fix. This is a parameter to the protocol and to the security proof. And to go from here to here, this is just the state distribution. And, as I said, I combine two things, parameter estimation. So this is the step where potentially we also abort the protocol. So in this step, Alice and Bob use the channel to send the, for example, in the BB84 protocol, to send the BB84 states, and Alice and Bob are checking whether the statistics is correct, whether the error, quantum bit error rate is below a certain threshold, and if it's not, then, or if it's above the threshold, they proceed. And that's what happens in this step. Now in the next step, we will do error correction, as I said, and have some x, and now there's a new, potentially new e, because during the error correction, as you know, some information leaks to ETH. So the information available to ETH will be different after the error correction step, and I'll just indicate that in this sense. But x, now what this means, x means Alice, and so the first system is always Alice's, the second Bob's, and the third ETH's. And so the second is now E. So the notation just should indicate Alice and Bob have the same value at this point, and they may still use the channel. So this is the error correction step, and this we will actually have to, so to do that, I will just refer to classical error correction results. This is not a topic of quantum cryptography. We use statements that are known or have been developed by information theorists who work in a completely classical domain. So you don't need anything quantum here, because x and y are already classical keys. So you notice this x and y, you should think of this as the data, the classical data Alice and Bob have after the distribution of state. So maybe I should be concrete. What are they in the BB84 protocol? In the BB84 protocol, you may think of x being all the information Alice needed to send the signal. So the basis choice and which bit, like you encode it into this basis, and y is everything Bob knows. So for example, what bit he received and what basis he chose. And now the final step is the privacy amplification step. And there, after that step, we will end up with an L-bit key, which I indicate. So this is still something that is, this is uncorrelated to the adversary, and the channel that we still may have a channel available is still true because it's infinitely available. And as I pointed out yesterday, we could now proceed further and here have a secure communication channel. I will not write this down. And also here we could have started earlier and have an authentication protocol. So up to here, maybe we didn't start having already an authenticated channel available. So maybe we had to run some other cryptographic protocol which generates the authentic channel. And that would be an authentication protocol. And here, as I said, we would use that in one-time path encryption. But this is what we already discussed, so we don't have to go into that. But just that you see the thing continues. We always just look at certain parts of this chain. Now, the part we will focus on is the QKD part is really that part here, from here to here. And now, in this part, this thing here, from, let's say, from here to here, this is, I would say, generic. So generic means, what I said yesterday, that if you have a new protocol, you only need to redo the part from here to here. And because here we are just talking about entropies and so on, and nothing will change. We don't need to know any more details. Maybe I should also, for completeness here, write, there's also some guarantee on this state, and the guarantee on this state is there's also some, this entropy is larger than some threshold, which I call now X conditional E prime. Now let's start with the privacy amplification step. And the privacy amplification step is based on a theorem that I now mentioned several times, it's called two-universal hashing. What is two-universal hashing? This is something that has been invented before in the purely classical domain. And as I just said, it had an important appearance in these first papers on privacy amplification that I just before indicated. where Uli was one of the authors. I think this paper that was really the first one used was one by, I think it was Bennett, Brassard, Crepo, and you, if I remember correctly, in '91. And however, and this is something you have to realize, in the classical theorems are here not applicable. So that paper was, of course, an important step, but the paper was classical in the sense that it also assumed that the information held by the adversary was classical. But there's now a quantum version of this, and I just emphasize that because if you're now taking some alternative, there are some alternatives to universal hashing which are called randomness extractors, and the so-called Trevisan extractor that some of you know is an example of that. If you want to use it, you need to redo the proofs. You cannot take the classical proof. So these things were proven to be good randomness extractors for classical, if the adversary holds classical side information, but that doesn't imply that it's also true when the adversary has quantum side information. So I will now give the quantum version of this two-universal hash lemma. Just call it two-universal hashing. And the statement is the following. So, so we have, this is now the most technical statement apart from the other parts that we had before. So I will assume I have a quantum state which has a classical variable and some E. And in order to be consistent with how we use it, I will immediately call it E prime because we will use it in this step here, and this T will be relevant. So we have, and be a density operator, and now, and I will assume that X, the alphabet of X is, okay. Actually, this can be arbitrary, I don't even need to specify that. And let F calligraphic be a suitable, and this I will not specify. I mean, if you read up the theorem, you will find a specification of what that suitable means, but for our purpose, you can just think of it, someone gives you that set. It's a set of functions from X, so they take as input the values that this system X takes. So here, this should be understood as the alphabet over which that defines these systems, and I will write concrete values with a small x, although in this case they don't even occur. Foo, and now I will assume that the output is an L-bit string. Okay. So what? Okay, let me write down the total thing, and you will see. Then the following holds, namely that if I look at the trace distance between, and now this is, okay, maybe for f chosen randomly, so by randomly I also, for a moment, think of it as uniformly from f. So I choose, I have a set of functions. So this calligraphic f is a set of functions which take as input that value here and output some key, you should think of length L. And now I generate the key by just choosing a function at random from this class, and then the following holds, namely that if I look at the density operator of the output of that function, so I apply f to x, so that's really what comes out by this thing. So f is now, I will now call f the hash function. It's the thing that you apply to get the key. If you look at this density operator, but you still consider also what the adversary knows, it's the E prime, and you also assume the adversary actually got informed what the choice of function is. That's important because in the use of this lemma, everyone will know what the function is. Then this density operator is very close to the one we want for security, namely we have an identity on the key system. Maybe I'll call that also the key system K, so that you can make the relation to this. So it's identity on K over 2 to the L, so that's a completely mixed state on the a completely uniform random L-bit key, and something here, E prime F. Okay, this distance is small, that's what it says, and small is now explicit. It's 2 to the minus 1/2, and okay, let me immediately make this connection to that. T x given E prime, then I will have to write this down, but I need less space here. It's minus L, where Tx E prime should satisfy this relation. I can write this here as well. So Tx E prime should be a lower bound on the mean entropy. Okay, then end let that. So, okay, well, let's briefly discuss that. So here I have a 2 to the exponent minus 1/2, a difference between the threshold, how large the mean entropy is at least, minus the key length. And what we want, of course, is that this whole exponent here is negative. Why do we want that? Because as soon as this exponent is negative, this becomes quite small. So we want the exponent to be negative, which means we want this t to be larger than L. But now what the lemma tells you, as soon as this is achieved, as soon as the t is larger than L, in other words, as soon as I have a guarantee that the mean entropy is larger than L, then what I calculate, so by applying the hash function to x, is a secure key. It has a very small distance to a state that is perfectly secure, as we have now seen that many times, where you have uniform key and it's independent of whatever the adversary knows. Yes.
I have seen a very different definition, or in my eyes, a very different definition of two universal hash functions of where you have like.
And this is not the definition of two universal hash functions. This is so the definition of what the universal hash function is basically this what I call suitable set. I don't want to state what it is because this would not be of no use. You should think if you use this. Let's say you can now black box use it. Someone tells you this is the set which satisfies this thing, and now as a user of that, you just now randomly choose a function from this set. Of course, now if you want to see the proof of the theorem, you need to know what is exactly this hash function. This is the universal set that you have probably seen. This is
I discussed it on Monday, yes.
Yes. All right. Yes. Yes. So actually, yes, I should point out the set. So although this is now a quantum theorem, so this E prime is quantum, and this doesn't follow from the classical case. The construction of the set is precisely the same that was shown by William on Monday. Yes.
I have two comments on this. First of all, you need an additive term with epsilon, I guess.
Oh, yes, right. You're absolutely right. There's plus epsilon here.
And then it seems that.
Actually, it's a 2 epsilon. Yeah. No, it's yeah. Yeah.
And then there is a difference between the classical and the quantum case. That's the factor 1/2, I think, in the exponent. Right? This is.
Okay. I don't remember how it's in classical, but
like
in
for
quantum,
you can only prove a weaker result, which is still good enough, but less than factor 2. It seems.
Yes.
Universal hash functions. Yeah.
I mean,
Or maybe I'm wrong.
okay, I don't remember the classical factor, but for quantum it's definitely there, yes. So actually it's to be expected, yeah, maybe I should also say, it's to be expected, so I just said that the classical results don't usually, so in general, there's no generic statement that tells you if you have something that is a good classical extract, it's also good quantum. So it would not be surprising that the quantum one is less good, although in the two universal hashing case I would be slightly surprised, so you need to check that, but that's at least the result for the quantum case. And you're right about this epsilon, so this smoothing parameter here has to occur here again. Okay, so now, okay, that was very technical, but even if you didn't now follow the technicality, what does it tell you? It tells you that it gives you a receipt on how you get from here to here, namely, what do you do? Does anyone, I mean, you probably know it already, putting together what Willie told you and what I told you now. So what do you do to get from here to here? What's the protocol, the privacy amplification protocol? Yes. What could Alice now do? So we are in that, Alice and Bob are in this situation. They have two identical keys. They have a large mean entropy, and they want to get a secure key up to some, let's say, epsilon here. Maybe this epsilon should now be a different epsilon than the one here, because that's the one okay. So the epsilon that is here is not necessarily exactly the same that appears at the end in the smoothing, so let's call it epsilon bar here. So what does Alice and Bob have to do?
They both apply like a classical function on their shared key.
Right.
Like
So
the same function, so f for the family.
right. They just do what is basically said here. That's absolutely correct. So Alice just says, let me. So of course, in the specification of the protocol itself, you have to already agree what is the set of function calligraphic f. So that's just fixed before you start. And now what Alice does, once you arrive at this point here in the last step of the protocol, is she just chooses randomly a function from this set of hash functions and tells Bob which function she chose. And we have seen also in Norbert's presentation that the description of the function can be quite long, but there are clever ways to reduce that description, and that's, as I said, the Trevisan extractor is an example of that, but there are also other things. So at the end, Alice has to tell Bob which function she applies. And then just both of them apply the same function f to the value x. So here they have just identical values. Alice has an x, this is called the raw key. This is whatever they got from measuring their quantum state. They apply this function, and of course, because they apply the same function, they will certainly get the same key. So here it's already guaranteed that the values are the same, and if you apply the same function, you will get the same. So they get the same key. And now the two universal hashing lemma tells you that this key will also be epsilon secure. More precisely, it's actually I could call that epsilon bar now related to this. So the two universal hash lemma tells you if you do that, the output, so that's now the key, f of x. Now this key will be independent of whatever the adversary knows. So what does the adversary know? The adversary certainly has this e prime, but in addition, because the function f was communicated, the adversary also knows the function f. So we have to really make a full statement, we have to say the key is independent of everything the adversary knows, which includes the function f. And that's what the two universal hash lemma achieves. So the two universal hash lemma does a big part of the job. It tells you, at the end, you don't need to care any longer about this security definition in your proof. Of course, you care about it to understand what security means. But in the proof, now we have to reduce the problem to this point where we say it's sufficient to ensure that Alice and Bob end up with what is called, as I said, a raw key, which has sufficient mean entropy. It's above a certain threshold. And so the threshold is basically just the amount of key you can extract. So what this also tells you is that the number of key bits you get is determined by this threshold. It just has to be a little bit smaller than the threshold. And this now shows what I also told you yesterday, that it's easy to make the security parameter smaller. Because let's suppose the key is 1 million bit, you want 1 million key bit. Now you have to ensure that the entropy here at this point is a little bit larger than 1 million. Let's say 1,500,000. But this means you have here already in the exponent 2 to the minus 1/2 times 500. So this gives 2 to the minus 250 would be a very small value. So it's very easy to make that epsilon small. Of course, there's this contribution from here, which you have to discuss in total. As I also mentioned, it's not so easy. But at least whatever is the contribution from the two universal hash lemma, this is completely unproblematic. It's very cheap to make this contribution smaller. So this means we are now here. So we have now achieved this step, and we can ask ourselves, how do we get to that situation here? But this is a good point to ask questions again. Is there any? So we have now done the last step. We are constantly simplifying our tasks. Now we have simplified the task of generating a key to the task of generating some classical information, x, a raw key, which has large mean entropy. That's what we have achieved now. Now we want to simplify it further. Let me say, here we still need to ensure Alice and Bob have the same thing, but let's suppose you only have a guarantee that x has a large mean entropy. but y is not identical to x. Now, as I said, what you're doing is, this is a classical problem. This has a priori nothing to do with Eve. Alice has x, Bob has y. How much information does Alice need to send to Bob in order to make sure Bob knows x? Does anyone know the answer to that question? So this is now a classical coding problem. Yes?
hx given y?
H and what h precisely? Max or min? It's almost here.
Min, I would guess.
If you look at this,
Then
yes, she wants everything to be determined. So these are the number of which she still needs to learn. So it's h max. But you are always right. So almost right. It's h max. So the number of okay, I didn't prove this statement. As I said, this is something one can derive from the definition, but that's what classical information theorists already did in the classical. So we now use the result. So I just should be clear, what are we using and what are we proving? Now we're just using as a black box the result that if we have a situation where Alice and Bob have two different classical variables and they want to have the same, then it's sufficient that Alice sends to Bob an amount of bit which is given by this entropy. I said that also yesterday briefly. So in other words, what happens here in the error correction is Alice sends a communication. So here we have communication, and the communication consists of h max epsilon x given y many bits. Classical bits. So this is just a classical communication. So Alice sends to Bob that. And I will call this communication C, just in order to refer to it. So now, what I've now said is that to get from here to here, the only thing that has to be done, of course that's, I'm not trying to trivializing it, I'm just saying on this level of abstraction, you can just think of it, there are procedures that allow Alice and Bob to send that. Again, there is this, so in all I say is this approximation up to log 1 over epsilon. So you might need to send a little bit more in order to achieve that, but that's negligible. Okay, so that's purely classical. So we know how to get from here to here. However,
maybe
yes.
something you should say, these epsilons are different, the different epsilons, and you choose them at the beginning and say, I want to have an error correction.
Yes, right.
You choose them, and then at the end you add up things in
right. So yeah, that's a good remark. So the epsilon that appears, so here in the max entropy there's an epsilon. Now for simplicity, I always use the same, which I can do. I mean, the only one that is not the same is the final one here. In a way. So if I want to optimize things, I would just put different epsilons and at the end see how do I need to choose them, what is the kind of cost of making that particular epsilon smaller, how does this contribute? And I think there are, I guess, okay, I'm not sure whether this is also covered by your frameworks, that you can optimize over the finite size parameter epsilon for the different things, but that's only something one wants to do, so you can do that. Yes. So you're right. I mean, there are choices. So the question how to choose this epsilon is, I think the way I will proceed is a priori we just leave it open. We say some small parameter, and then at the end we have a big formula where all these epsilons enter, and we try to optimize them. Okay, but now there's an important thing here. We have this threshold Te prime, and what would be useful, this is not necessarily the same as here. So we got from here to here, but this T is different. So does anyone have an idea what we can say about, let's suppose you only have this T here. So you start from here, you have a guarantee it's larger than a particular value. What guarantee do you get here? What's the new T, it's given E prime, that I have to write down here? Does anyone see that? So, in other words, what I'm saying is that here I have a guarantee that the mean entropy is larger than some value. Let's say it's larger than 1 million. Now I do error correction. How large is the mean entropy now? Yes?
less than previous one?
It's less, right? That's correct. That's exactly the data processing inequality because Eve learned C. So you should think of this E here it's the old E, the one that was here, plus the communication C. So that's a correct answer, and that's true, that's generally true, and this will be lower. However, actually it's not now the useful direction, because I want to, if it's lower it could be 0, and then it's useless. So the question is, can I also bound it from below? And now you will see, I mean, you basically now, for your answer, use the first line here, but you could have used the second line. And so what the second line tells you is that I can, okay, this is maybe not a good style for pedagogically, but I will now just erase things here and replace things. So I replace the A by an X, which I can do. This is just a special case. And I replace the B by E. And the C is already chosen cleverly as C. So what is E prime is that thing. So in other words, what this inequality tells me is that I'm interested now in this thing. I want to bound that. So that value here I want to bound, or I want to know that bound here. That bound will be given by this X thing here, which is bounded by T. So I could even write here TE given Tx given E. That's the bound I already have. That's where I start from. So I have a lower bound of this, so I just need to put this term on this side. I just need to subtract this term. So in other words, what I've shown now, okay, now it gets a bit crowded, but this is the last thing I will add to this picture, is using this chain rule, I can argue that this thing is larger than Tx given E minus the amount of communication, minus H max of C. But what is H max of C? C consists of that many bits, which means H max of C is certainly not larger than that value here. So I can also write this, and if I choose it optimally, it's just equal. I can write this as Tx given E minus H max of X given Y. So what I've now achieved is the following. I have now a way to say that if I know that the mean entropy is large and Alice and Bob don't have the same strings, I can still get there, and I can calculate the key length. So let's now combine these statements. And that will be almost the final statement before we move to the non-generic part. So let's now put the two things together that we just did. So again, let me use this notation where I use an approximation if it's just distinct by some small log 1 over epsilon. So what we are interested in is the key length. How much key can we produce? That's what we are interested in. L. And ideally we want to have a lower bound. But if it's at the end even larger, we are happy. So we want to show that at least it's a certain length. Now, the key length, okay, actually I realized sometimes it's not good to put it as a lower bound because in a concrete protocol we will choose it specifically and then you always cannot, I can choose it that way, but of course what I'm showing here is just for that protocol it has that length. It doesn't exclude that there may be a better protocol that produces a larger length, but I don't need to say that. So for that particular protocol, I can choose the L to be of the following size. So let's again start from here. So the L, as we said, or you can still read it here from the hash lemma, the L has to be a little bit larger than this, and then the key is secure. So I can choose the L to be, and as I said, this little bit I will just put into the approximation. I can say that if the L is a little bit larger than T x given E prime, then it's secure. So I can choose the L to be that. But now I also know that the T x E prime is larger than, and okay, I think we already wrote this here.
Red.
Yes, oh yeah, the red thing. So I can just replace this by T x given E minus H max x given y. But the T was a bound on the mean entropy, so I can just choose the optimal bound. Then it's an equality. Mean epsilon x given E minus H max x given y. And as I said, this is always up to this log. When you write it here, plus minus log O, so it's up to an additive term log 1 over epsilon. So this means it's of the order of that. So that's our result. So we know the key length of this generic part here is given by this formula. And this has now reduced the complexity enormously of the proof, because now we can say the only thing we need to do in this non-generic part is to somehow find a way to distribute the state such that at the end you can guarantee that you have a bound on this quantity here. And that bound will tell you how much Q. So this is the, let's say, key form. This is the, regarded as a generalization of the rate formula, or the sometimes called the Devika-Quinter formula in the asymptotic case. This is the one-shot version of that. So whatever scenario you have, whatever key distribution protocol you invent, these are the entropies you need to calculate. And now you see you don't need to know anything more about the state. You just need to make sure you know these entropies. That's already a simplification. Now for the last quarter of an hour, I would like to now make the connection to what Norbert did, which is actually the way to get these quantities. So now, you know this is the relevant quantity. How do you ensure that whatever state you distribute here satisfies, or how do you calculate that? How do you guarantee that this is good? So in other words, just to be clear, what is the order? So you can, for example, say, I want to have a key of length L equal a million. And then what this expression tells you, you now need to make sure in this distribution phase, what comes out is a state such that this is at least a million. So that's what you need to do. Okay, now we come back to this big problem we had, that generally an adversary can mix up things. So the state for which we are evaluating these entropies could be still an arbitrarily complicated state. But now there are, in quantum information, or in the history of cryptography, there were several developments that allowed us to overcome this problem. And there are today, I think, approaches where it's hard to decide whether one is the best one. I mean, there was a continuous development, and some have advantages and some look more promising than others. One of them is called entropic uncertainty relation. And this is a method that will never use von Neumann entropy. It will directly do stuff on the level of mean and max entropies, but I will not go into that, just that you have heard the term. So there's entropic uncertainty related proofs. The reason why I'm not going into that is that they're less generic. They only work under situations where the measurements that both chooses are such that certain entropic uncertainty, like some entropic generalization of the Heisenberg uncertainty principle applies, and this is not generally optimal. So these proofs are good, for example, for the BB84, but generally they don't give you, even in the asymptotic case, the optimal bounds. There are two other methods. One is called the entropy accumulation theorem, and I will just have to focus on one method. I will not talk about that, although it's one that is now looking very promising in the sense of giving very good finite size rates. And it's based on the idea that you just generalize this asymptotic equipartition. Okay, it's no longer here. So I showed you the asymptotic equipartition property before, which says for an IID state, the mean entropy is related to the von Neumann entropy. The entropy accumulation theorem tells you that even if the state is not IID but satisfies certain Markov type properties, you still have this property very roughly. So that's what it does, just that you see where it acts on. And the other method is the Definetti theorem. You may hear more about that. Maybe Rotem is saying something about that because it also plays a role in other things, although it's actually hard to apply it in generalized situations like device independence. But the Definetti theorem is conceptually maybe the best way to understand what's going on or why we can even reduce the complexity. And the idea is to use a theorem which is due to Definetti, and it's again a quantum version of that. So Definetti was a classical probability theorist who developed the theorem in the 30s of the last century, so it's an old theorem. But the quantum version is of course more recent, and I will immediately give you the quantum version. So the quantum version is the following. So suppose you have a bag of quantum systems. System S1, S2, S3, S4, and so on. Sn for capital N. And by a bag, I mean they are not ordered. Or in other words, it's like when you do in statistics experiment, you pick things from a bag. So you should think in that way. Now, of course, if I write them down in an ordered way, I mean, whenever I write something, I have an order because I write from left to right. I could still, I would say they are permutation symmetric. That's the same as saying they are not ordered. Now let's suppose I pick out a subset of these systems. Let's say I have here a subset randomly in that sense, because there's no order, it's necessarily random in that way. So now I look at the state of these subsystems. So the blue set, it consists of S1 to Sn, where n is smaller than n, so it's a subset. Now, what the Definetti theorem tells you, this is actually surprising because I didn't assume anything about this. Okay, I assumed something. I assume all these systems have the same dimension. So I assume that the dimension of all these systems Si is fixed and finite. But now the Definetti theorem tells you that if you now look at the random subset of this system, then the state will be an element of the convex combination of states which are of IID form. So it's some sigma tensor n. And there is, again, this time it is not exactly true, it's true up to an epsilon. I will, again, using the kind of notation, I have just put the epsilon here to say this is a set, and we disturb the set a little bit by an epsilon. And this epsilon is actually small. It's small, namely it's 2 to the minus something like, very roughly speaking, n minus n. But this is a simplification, but it gives you the order of magnitude by n times d squared. So it tells you at some point in some appropriate regime, it's going exponentially fast to 0. There's actually a slight cheat. These states are not exactly ID states, they're so-called almost ID states, but on the level on which we are discussing that, this is now not relevant. So what the Definetti theorem so by the way, what does a convex combination mean? It just means it's with so the sigma is not specified. The sigma is just some state of one subsystem. And the convex combination means is that the Definetti theorem tells you that the state of this total system is such that as if it was, as if you prepared it by choosing with some unknown way a sigma, and then just making n copies of it. And you see, this is, of course, just the IID property. So the Definetti theorem tells you, as soon as we don't look at all systems, but only a subset and choose them randomly, we are in the very nice IID situation. This is a very strong simplification again, because it now allows us to assume and to do the ID stuff and so on. However, there's still the convex combination, so we don't know what this sigma is. So we are not yet there, we cannot yet apply the asymptotic exponential. How do we determine the sigma? This is where parameter estimation comes in. So because here check, so in this state distribution you check what is, so the state distribution is really the part that you have seen in the BB84 protocol, for example, but this is different from each protocol. But in the BB84 protocol, for example, you check whether the quantum bit error rate is larger. Now, if you check that and apply the Definetti theorem based on, on the state conditioned that this check has succeeded, then this convex combination is constrained to sigmas, which have the property that okay, let me erase. So you additionally get the guarantee that the sigma is in a certain set A. And the set A is the set of potentially accepted states. In the case of BB84, it's the state that it's a set of all sigmas such that if you indeed would prepare n systems in the state sigma and measure the quantum bit error rate, you would get a quantum bit error rate that is accepted. So, quantum bit error rate of this sigma, if you apply this n times or so, is below, for example, a certain threshold t that you fix. And this now depends on what thresholds you put and so on. So in other words, it's not a problem that this sigma here is arbitrary, because by the parameter estimation procedure, we constrain it to be in this state of acceptance. So now what we have at the end is we know our system can be assumed to very good approximation epsilon to be in an IID state for a state which is in this set. Now the final thing is to return to the asymptotic equipartition property and say, now as we know that the state is of this form, we can just evaluate the mean entropy, which is of interest, namely this thing, and replace it by the von Neumann entropy. So this last step tells us just evaluate instead of this. So we now go to the asymptotic limit, of course, for the moment, but you can do that, there are finite size versions. You can now, by the asymptotic equipartition theorem, replace this by the von Neumann entropy of x given E for this sigma. And here you do the same. So this will just, so the max entropy also satisfies the asymptotic equipartition theorem. It holds for both the mean and max entropy. So you have here also the sigma. And because the sigma is in this set, and of course you want to be sure that the protocol is secure, you don't know more about the sigma, you have to do a worst case consideration, minimize over all sigmas in this set, and then calculate this difference here. And this is at the end the formula you have seen from Norbert. I guess here is where our things now merge. So you have a minimization over these sigmas and this formula which was the rate formula. I mean, it's a rate formula because if you look at the asymptotic equipartition theorem, I divide this thing by n, where n is the number of individual systems. Okay, no, this was now the proof is at the end technical. This was a high-level description, but I think what you should realize is the following. Of course, it takes a lot of time to understand all the details of the proof. However, because of the modular character of the proof, you should now, at least from this lecture, be able to go into the individual parts and understand how they fit together. And so a good advice, if you really want to understand the proofs in detail, is to first learn about these entropies. They will appear on the technical level. And then once you have them, you can look at these steps individually. You can now study, if you want, the two universal hash lemma or the error correction. And at the end, the way things fit, or these Definetti theorems, and they all are individual ingredients which can be understood independently of each other. So to understand the universal hash lemma, you don't need to understand the Definetti theorem and so on. So you can look into these parts and try to get an understanding. And the goal of the lecture was more to see how the parts are fit together, so to have a kind of a roadmap in your mind of where to find the individual things. Okay, so to conclude, I just want to mention that the status of security proofs is now such that for most protocols which are device dependent, we will hear about device independence from Rotem. I guess that's still the plan, and that's her topic mostly. Yes. It's actually much more difficult because there we can not. So here what we assumed when we, for example, this was part of Norbert's thing. Then you went to so what is the state to distribute? You of course assume you know what measurement is applied. For example, the measurement with respect to the BB84 basis. In the device-independent setup, you don't know what the measurement is that is applied. And so it's not clear that the measurement is even an individual measurement. It could be that the measurement spans over many subsystems, so it's not even clear that you have individual measurement measured so that the individual results you see belong to individual subsystems. And this makes it very hard to apply arguments like this, where we still want to talk about subsystems. We want to say there was something coming from that subsystem, something else from that, and so on. So there are still big conceptual challenges in proving and understanding the security of device-independent cryptography. In the case of device-dependent cryptography, we understand it very well on the conceptual level. However, there are also very big open questions and challenges regarding how do we now cleverly evaluate these formulas, and that's of course Norbert's domain. There's a lot of work to be done there as well, but there the work is more on the here. I think this part is understood relatively well. So on the concrete level of protocols, it's to optimize, find clever protocols that are good in the finite size regime, and it's also this Definiti's theorem, although there is this exponential dependence that I mentioned. The exponential dependence is not as good as one could hope in the finite size regime. So there's also a lot of conceptual work still going into improving these methods or finding different methods. As I said, these entropy accumulation theorems, which would improve the parameters. And these are purely information theoretic contributions, which again, surprisingly have usually different applications. For example, in black hole physics. Question. We should probably have a bit of time to move. Okay, so enjoy the afternoon.